In this video, we solve problems 1 and 2 from quiz number 8 from the fall 2020 semester. This covers standard L27, which is about solving initial value problems with the Laplace transformation. This is the second standard covering solving initial value problems with the Laplace transformation. And these particular initial value problems have these characteristics. The differential equations may have forcing functions that depend on the heaviside functions or heaviside function, or Dirac delta, or the differential equation may have variable coefficients. Or I guess we could have a combination of both of those. That would be fine. But this is the first equation and the first set of initial conditions as well. We see we've got a delta function in the forcing function, and we're asked to find y of t. So we always start in the same way. We let the Laplace transform of little y equal big Y, just to introduce our notation so everyone knows what we're talking about. And then we take the Laplace transform of both sides of the differential equation. So let the Laplace transform of little y equal big Y. And then we remember the Laplace transformation is a linear operator. So we'll have the Laplace transform of y double prime minus the Laplace transform of y prime minus 2 times the Laplace transform of y equals the Laplace transform of t minus 1 plus the Laplace transform of this delta at t minus 2. The Laplace transform of y double prime is s squared times y of s minus minus s times little y at 0 minus y prime at 0. And then we're subtracting the Laplace transform of y prime. Don't forget your parentheses there. The Laplace transform of y prime has two terms. Oops, that's an s to the first times y of s minus little y at 0. Then we're subtracting 2 times the Laplace transform of y. And that is equal to the right-hand side. The Laplace transform of t is 1 over s squared. We have the Laplace transform of -1, which is -1 over s, plus the Laplace transform of delta at t minus t naught. Remember, that's e to the negative s times t naught. Here, our t naught is equal to 2. So this is e to the negative 2 times s. Okay, so now we just have to substitute in our initial conditions, or the values of y of 0 and y prime of 0 from our initial conditions, and then we will solve for y of s. So y of 0 turns out to be 0, and y prime of 0 turns out to be -1. So what we get here is s squared times y of s minus a -1, that's +1, minus s times y of s minus 2 times y of s equals 1 over s squared minus 1 over s plus this exponential function. And if we add or subtract 1 from both sides and factor out the y over s over here, we have this. Oops, there we go. And s squared minus s minus 2 factors. Need two numbers that multiply to give me -2 that add to -1, -2, and +1 will work. Now I want to get y of s by itself. So I'm going to divide both sides by 2, or s minus 2 times s plus 1. But that just means I'm going to divide each of these terms by that expression. So we'll have -1 over s minus 2 times s plus 1. And this 1 over s squared, rather than dividing by that expression, I'm just going to multiply by 1 over that. So that will give me an s minus 2 times s plus 1 in the denominator there. And then over here, we're going to do the same thing. We have a -1 over s, and we're multiplying by 1 over s minus 2 times s plus 1. And then we have that exponential function. And we need that over s minus 2 times s plus 1 as well. Oops. So from here you have some options. You can use partial fraction decomposition for this and this and this. And then whatever partial fraction decomposition you have for this, you can just multiply it by -1 to get the partial fraction decomposition for the 1 over s minus 2 times s plus 1. That's one way to do it. That requires using partial fraction decomposition 1, 2, 3 times. I don't think I want to do that. Most of the time I don't simplify these things, but this time I think I'm going to combine these two together at least. So I will multiply this one by s over s, and then I'll have a common denominator. So then y of s can be written this way. I've got -1 over s minus 2 times s plus 1. And then I have a 1 minus s over s squared times s minus 2 times s plus 1. And then we've got the exponential times s minus 2 times s plus 1. Okay, so I'll use partial fractions for this and for this. I'll call this star, and I'll call this double star. So let's handle this starred expression first. So we have -1 over s minus 2 times s plus 1. That's the same as a constant over s minus 2 plus a constant over s plus 1. And we multiply both sides by that denominator. And these reduce, and these reduce. So we end up with -1 equals a times s plus 1 plus b times s minus 2. And then we use this equation to solve for a and b by choosing values of s that cause each of these factors to be 0. When s equals -1, this guy is gone. Well, -1 plus 1 is 0. So on the left-hand side, we have -1 equals b times -1 minus 2. So that's -3 times b. So b equals +1/3. And this guy is 0 if s equals +2. So we still have -1 on the left-hand side. And we'll have a times 2 plus 1, which is 3. And then we have b times 2 minus 2, which is 0. So we just end up with this, which means that a equals -1/3. So the partial fraction decomposition for this expression is -1/3 over s minus 2 plus 1/3 over s plus 1. Okay, now we want to use partial fractions for this piece. Now I've got a repeated linear factor here. So we'll have a over s plus b over s squared for that repeated linear factor, plus c over s minus 2 plus d over s plus 1. And we're taking each of these terms and we're multiplying it by the LCD, which is always the original denominator. Okay, then we take that and we reduce common factors in the numerator and denominator. And then we're left with this equation. We have s minus 1 over here equals a times s minus 2 times s plus 1 plus b times s minus 2 times s plus 1 plus c times s squared times s plus 1 plus d times s squared times s minus 2. Now if we let s equal 0, a lot of these factors are going to go away. they'll be zeroed out. If s equals 0, the left-hand side is 1 minus 0, which is 1. Then we'll have a times 0, c times 0, and d times 0. So this will be 0, this will be 0, and this will be 0. The only one that's not 0 is this one. So I'll have b times negative 2 times positive 1. So that's going to be negative 2b equals 1. So b must be negative 1/2. Then I'll let s equal, positive 2 in order to cause s minus 2 to be 0. Well, then I'll have 1 minus 2 is negative 1. And if s minus, or if s is equal to 2, then s minus 2 is 0. So this is a times 0 plus b times 0 plus d times 0. The only part that's not 0 is this term. S is equal to 2. So we're going to have c times 2 squared, which is 4. 4 times 2 plus 1, which is 3. 4 times 3 is 12. So c is negative 1/12. Then we'll let s equal negative 1 to cause the s plus 1 factor to be 0. 1 minus a negative 1 is 1 plus 1, which is 2. So we'll have a times 0 plus b times 0 plus c times 0. The only one that's non-zero is this term over here. So we'll have d times negative 1 squared, which is positive 1. And negative 1 minus 2 is negative 3. So we'll have negative 3 times d equals 2. So d equals negative 2/3. Okay, so that means our y of s can be written this way. We had the partial fraction decomposition for this first expression, which was negative 1/3 over s minus 2 plus 1/3 over s plus 1. Okay, so that's the first partial fraction decomposition. And then we had plus this expression, which has this partial fraction decomposition. Oh, we didn't find a, did we? We got b, c, and d, but we didn't find a. We need to choose another value for s to get a. So let's choose s equals 1. If s is equal to 1, we'll have 1 minus 1, which is 0. Then we'll have a times 1 times 1 minus 2, which is negative 1, times 1 plus 1, which is 2, plus b times 1 minus 2 is negative 1. 1 plus 1 is 2, plus c times 1 squared times 1 plus 1, which is 2, plus d times 1 squared times 1 minus 2, which is negative 1. So we've got this equation involving a, b, c, and d, but we already know b, c, and d. So we have negative 2a plus all of this. Let me add that negative 2a to both sides. So we'll have 2a equals negative 2b plus 2c minus d. And b is negative 1/2. c is negative 1/12. And d is negative 2/3. We're subtracting that, so that means we're adding 2/3. This is going to give me a 1 minus 1/6 plus 2/3, which is the same as 4/6. So I have 4/6 minus 1/6, which is 3/6. So that's 1/2 plus 1. 1.5 is 3/2. And that means that a is 3/4. Okay, so the partial fraction decomposition for this expression, again, is a over s. So that's 3/4 over s, plus b, which is negative 1/2 over s squared, plus c, which is negative 1/12 over s minus 2, plus d, which is negative 2/3 over s plus 1. And you could combine these. I've got a 1/3 here and a negative 2/3 there. And then there's an exponential expression. Before we combine them, let's add that exponential expression. Then we had e to the negative 2s times, where is it? Positive 1 over s minus 2 times s plus 1. Well, we have a decomposition for negative 1 over s minus 2 times s plus 1. It's this, where a equals negative 1/3 and b equals positive 1/3. If I multiply that by negative 1, I'd have a positive 1/3 here and a negative 1/3 here. So the partial fraction decomposition for the expression that's multiplying this e to the negative 2s is 1/3 over s minus 2 minus 1/3 over s plus 1. Okay, so I was just able to use that same partial fraction decomposition twice. I just took that and I multiplied it by -1. All right, now we can combine like terms. I've got an s minus 2 term here and another one over there. So I've got 1 over 3. I multiply that by 4 over 4. That's -4 over 12 over s minus 2 minus 1 over 12. -4 over 12 minus 1 over 12 is -5 over 12 over s minus 2. So I've taken care of these two guys. And then for the 1/3 s over s plus 1 minus 2/3 over s plus 1, that's going to be 1/3 minus 2/3 is -1/3. And then we have 4/3 over s and a -1/2 over s squared. Okay. Plus this exponential expression times this. Okay, now I think we're ready to compute the inverse transform. Now remember, this one has the form e to the negative as times f of s. And the inverse transform of something that looks like this has this form. First, you find the inverse transform of f of s. That's going to give you f of t. But then you replace all of the t's with t minus a's, and then you multiply by the heaviside function at t minus a. So what you get is f of t minus a times h of t minus a. Okay, so for y of t, that's the inverse Laplace transform of y of s. We'll get this, -5 over 12 times the inverse transform of 1 over s minus a, where a is equal to 2. That's e to the 2t. This is the same form. It's 1 over s minus a, where a equals -1. So we bring the constant of -1/3 down. The inverse transform of 1 over s minus a -1 is e to the -1 times t. The inverse transform of 1 over s is just 1. So the inverse transform of 3/4 over s is 3/4. The inverse transform of 1 over s squared is t. So that's going to be a -1/2 times t. And then this piece is the one that requires the most work because we have to apply this expression, this result. Through pattern matching, we see that a is equal to 2. So we can write this down. First, we need the inverse transform of f of s, which is 1/3 e to the 2t minus 1/3 e to the -1 times t. But then we're going to replace all of our t's with t minus a's, where a is equal to 2. So it's going to be replacing t with t minus 2. And then we take that whole thing and we multiply by the heaviside function at t minus 2. Okay, so that's our function y of t. We want to write it as a piecewise function. Well, there will be two intervals, one interval from 0 to 2, the other interval from 2 to infinity. On the interval from 0 to 2, we just have this plus this times 0. So we just end up with that function there. Because remember, the heaviside function is 0 until you get to 2, and then it's 1. That's the heaviside function at t minus 2. And then on the interval from 2 to infinity, we have this plus this times 1, because on the interval from 2 to the infinity, the heaviside function is 1. So I'm just multiplying this by 1. So it just ends up being this plus this. Okay, and that's our y of t. So that's the answer for problem 1. Now let's look at problem 2. Now this one was a little bit harder. Well, actually, let's be honest, it was much harder. But there's actually a little bit of a trick to it. At the end, it might seem that it can't be solved, but it actually can be solved. We just have to use integration by parts. And if we use integration by parts in just the right way, it turns out to work out quite nicely. So here is the differential equation. We have 3 times y double prime plus 2t times y prime minus 2 times y equals 6. And we're given these two initial conditions. Y of 0 is equal to -3, and y prime of 0 is equal to 2. Notice that this has variable coefficients. That means we're going to use the result that we have for computing the Laplace transform of t times f of t, which involves the derivative of a Laplace transform. So we start in the same way that we always do. Introduce our notation. And then we take the Laplace transform of the differential equation. So we'll have 3, because the Laplace transformation is a linear operator, 3 times the Laplace transform of y double prime plus 2 times the Laplace transform of t times y prime minus 2 times the Laplace transform of y equals the Laplace transform of 6. And this is the one piece you might want to work out separately. Some students want to work this out separately as well, so I'll just do that. That's the Laplace transform of the nth derivative where n equals 2. So it has 3 terms. So we'll have s squared times y of s minus s to the first times little y at 0 minus y prime at 0. And then our initial conditions are that y of 0 equals -3 and y prime of 0 equals 2. This simplifies to s squared times s squared times y of s plus 3s minus 2. Okay, so that is all multiplying that 3 there. Don't forget the 3. And then for the second expression, we've got t to the first times y prime. N is equal to 1. That's the power of t there. And this is the result that we need. The Laplace transform of t to the n times f of t turns out to be -1 to the n times the nth derivative with respect to s of the Laplace transform of f, which is f of s, and then we take the nth derivative with respect to s. So that's exactly what we're doing here. This is -1 to the first times the first derivative with respect to s of the Laplace transform of y prime. And the Laplace transform of y prime is s to the first times y of s minus little y at 0. And little y at 0 is -3. So we have -1 times a derivative that requires the product rule. This is a function of s times a function of s. So we will have the derivative of the first times the second, y of s, plus derivative of the second times the first, plus the derivative of +3 with respect to s, which is just 0. So I would distribute that -1. And we have that. Okay, I think with this expression, in this expression, we can substitute into the differential equation and write that differential equation as a first order differential equation involving y. So we have 3 times the Laplace transform of y double prime, which is right there, s squared times y of s plus 3 times s minus 2. And then we have 2 times this quantity, -y of s minus s times y prime of s, minus 2 times the Laplace transform of y, which is y of s, equals the Laplace transform of 6, which is 6 over s. Okay, now let's simplify this equation. We're distributing that 3. And since we notice that it's first order in y of s, I will rewrite it this way. I'll put my y prime term over here. So that's taken care of. Oops, has a red cap, but it's actually a black pen. That's not what I wanted. There we go. Then I want the y of s terms. I've got a 3s squared times y of s minus 2 times y of s minus 2 more times y of s. So that ends up being 3s squared minus 4 times y of s. And that equals 6 over s. And then I want these terms to be on the other side as well. So I will subtract 9s from both sides and subtract 6 from both sides. Well, this looks like a first order linear equation in y of s. So we'll divide everything by negative 2s to get the coefficient of y prime to be a 1. Now where I have a fraction here, I'll just multiply that by 1 over negative 2s, because dividing by negative 2s is the same as multiplying by 1 over negative 2s. And then we end up here. And of course we can simplify. So we have y prime equals, or y prime plus, excuse me, 3s squared over negative 2s is negative 3 over 2 times s. Negative 4 over negative 2s is positive 2 over s. The 2 goes into 6 3 times, so we'll have negative 3 over s squared here. Then the negative over a negative is a positive, the s is reduced, and then the negative 6 and the negative 2 reduced to 3. So we have this. So this is first order linear in y prime, or in y, excuse me. Now we want to solve this first order linear equation for y of s. So this is our p of s. Now in order to solve this, we need to compute the antiderivative of p of s. That's the antiderivative of negative 3 over 2 times s plus this. So we'll use the power rule, add 1 to the exponent, divide by the new exponent. And then I have 2 times natural log of the absolute value of s plus c. We'll choose that c to be 0 because we only need one integrating factor. We don't need infinitely many integrating factors. So our integrating factor for this differential equation is this. It's e to this power. So that's e to the negative 3/4 s squared plus 2 times natural log of the absolute value of s. Now there are a couple of properties from algebra that we're going to use to simplify this. In algebra, if you had 2 power functions, they have the same base, you'd add the exponents. Well, we can do that backwards here. If you have a sum of 2 exponents here, that makes that e to that first number, or first expression, times e to the second expression. Now you might be tempted to reduce the natural log and the base e because those are inverse functions, but they don't just reduce right here, not with that 2 out front. So you have to use this property from algebra as well. If you have a constant in front of a natural log of a, you've got to bring that constant inside as a power for a. So this is actually natural log of s squared. So we'll have e to the natural log of the absolute value of s squared, and those will reduce, and that'll give us an s squared as long as s isn't 0. And now we're here. Okay, so that's our integrating factor. Now, if we take this differential equation and multiply by the integrating factor, then the left-hand side should be the derivative of y of s times the integrating factor. So let's see if that checks out. So the integrating factor is s squared times this exponential. And then I'm taking this and I'm multiplying it by this. I think I'll take each term and multiply it by this. So if I take this negative 3 over 2 times s and I multiply it by that, I'm going to get negative 3 over 2 times s squared is going to give us an s cubed. And then we'll have plus 2 over s times s squared. That's going to give me just a 2s times the exponential e to the negative 3/4 s squared times y of s. And then we're going to have this on the right-hand side as well. And here's the right-hand side. We're focused here. This is our differential equation that we're multiplying by the integrating factor. That's our dE. Call it dE star because we already had a different dE that we're trying to solve. I'm taking this and I'm multiplying it by that. So if I take this and I multiply it by that, the s squareds are going to reduce. So I'll just have a negative 3 plus 9 over 2 times s squared plus 3 over s times s squared is just going to give me 3s times e to the negative 3/4, almost put 4/3, negative 3/4 s squared. Okay. Now the claim is that if we multiply by the integrating factor, then the left-hand side should be the derivative with respect to s of y of s times the integrating factor. And I think I'll write this differently. I think there's a sign error somewhere. I just caught it. So there's a 9s plus minus 6. So I'll subtract 9s from both sides and then add 6 to both sides. That would make that a minus, which would make that a minus. Okay, that's what I wanted. All right, so the right-hand side is this, negative 3 minus 3s plus 9 over 2 times s squared times this exponential. Okay, now the claim is that these are equivalent because the left-hand side is the derivative of this product, where here's my first function and here's my second function. According to the product rule, I should have derivative of the first times the second, which is what I have here, plus derivative of the second times the first. The way we can check and make sure this is actually equal to this is just check that the derivative of this is actually equal to this. So let's check. So I have the derivative with respect to s of s squared times this exponential. According to the product rule, we should have derivative of the first times the second plus the derivative of the second. In this case, the derivative of an exponential is the exponential times the derivative of the inside. So we'll have negative 3/4 times 2s, which is negative 3 over 2 times s. That's derivative of the second. Don't forget to multiply by the first, that s squared. And when we simplify that, we end up with 2s minus 3 over 2 times s squared, which is s cubed. And we can factor out the exponential function. Is that the same as what we have there? It's in a different order, but yes, those are the same. So this checks out. This actually is equal to this. Now this is where many people might give up. I almost gave up myself. I said, oh my goodness, how are we going to do that? I've got a constant times this expression here, and that looks like an error function. And we know we can't take the antiderivative of that using the error function. But I thought, you know what? This is a textbook problem. It's supposed to work out nicely. I bet there's some way that I'll get rid of that -3. I bet it goes away. And it turns out that it does if we use integration by parts. So we're trying to get y of s by itself, and we have it multiplied by this, and then we take the derivative of that result. So to undo that differentiation, we take the antiderivative of both sides with respect to s. And then we have the left-hand side is just this product. And the right-hand side looks to be an impossible integral. But it turns out it's actually not. Now, I think we all know that if we just had that 3s times this, we could use a u substitution, because the derivative of the inside here is going to be a constant times s. So if I have a constant times s times this exponential, I could do it with a u sub, no problem. And then for this s squared, I'm thinking maybe if I use integration by parts with that, I could do that. That might work. So the only issue here is this -3 times this. So I'm going to just set that aside for right now. Let's distribute the exponential. And we'll leave this over here on the side just for a moment. And then this I want to write differently. I want to write it as 9/2. I've got s squared minus 3s here. But I want to write it even more differently than this. If I were to use integration by parts, I want to choose part of this to be u, everything else to be dv. Now dv has to be something that we can anti-differentiate. So dv can't be this exponential because we don't know the antiderivative of just this function by itself. This one doesn't actually have an elementary antiderivative by itself without any extra factors. So we would be in trouble if this was our dv. But we know if there was just an s multiplying it, then we could use that as our dv, because then we could use a u substitution to compute the antiderivative. So what we'll do is we'll rewrite this in a different way. We'll write this as 9/2 times s minus 3 times s times this exponential. And we'll let this be our u, and everything else is dv. So u is 9/2 times s minus 3. We need to compute du. We need to anti-differentiate dv in order to get v back. Okay, well, the derivative of this with respect to s is positive 9/2 times ds. Now the antiderivative of this, we could use u substitution if we wanted to. We could let w equal this and then adjust the constants. But I would rather just think through what this would have to be. I know that the derivative of e to the -3/4 s squared is going to be a constant times s times e to the -3/4 times s squared by the chain rule. So I just need to figure out what that constant would have to be so that this coefficient will be a 1. Well, the derivative of this would give me a -3/2 times s times this expression here. So it'd have an extra -3/2 factor out front. To compensate for that, I'm going to multiply by -2/3. Take the derivative and see if you get this. If I take the derivative of this times this, I get the -2/3 times the derivative of the exponential, which would be the exponential times the derivative of the inside. And the derivative of the inside is -3/2 times s. -3/2 times -2/3 is going to be 1 times s. So it's going to give us this. That's great. Now watch this. We'll use integration by parts, multiply across that diagonal, multiply across that diagonal, and subtract. So we get u times v, which is this, -2/3 times 9/2s minus 3, minus the integral of v times du. So we're actually subtracting a negative, so that means we're adding 9/2 times 3, or 2/3. The 2's are going to reduce, and we'll have 9/3, which is 3, times the exponential. times ds. Do you see why that's so great? Do you see what happened? Because we used integration by parts for this guy, we ended up with this positive 3 times this exponential here and a negative 3 times the exponential over here. So those guys reduce, and we just end up with this plus c. We should add a c because those were indefinite integrals. So this becomes, if I distribute that negative 2/3 here, we get negative 3s, and the 3's will reduce there, plus 2 times e to the negative 3/4 s squared plus our constant, and this is equal to y of s times our integrating factor. Okay, great. So we thought it was impossible to integrate, but it actually wasn't. We could use integration by parts, and then the impossible term disappeared. So now if I want to get y of s by itself, I will divide both sides by the integrating factor. This reduces with this. And watch what happens here. We end up with y of s equals this divided by this, just this whole expression divided by this. The exponentials will reduce. And so we'll have negative 3s over s squared, which is negative 3 over s, plus 2 over s squared, plus c divided by this. So I'll have an s squared in the denominator, and I'm dividing by an e to the negative 3/4 s squared. So I can bring that up to the numerator. That's going to be e to the positive 3/4 s squared. Now, if y of t is a piecewise function of exponential order so that we're guaranteed that y of s exists, then as s goes to infinity, there should be an s squared there, y of s should go to 0. So let me write that down. Remember, we have this theorem. If y of t is a piecewise function of exponential order, then the Laplace transform of y of t exists, and the Laplace transform of y of s satisfies this. As s goes to infinity, the limit has to be 0. Well, as s goes to infinity, I've got this exponential over a polynomial in s. The exponential will definitely grow faster than that. So this would go to infinity if c were anything other, well, if c is positive, this will go to infinity. If c is negative, this will go to negative infinity. So this is going to approach some number other than 0 if c is anything other than 0. So the only way that y of t could be a piecewise function of exponential order so that we're guaranteed that y of s exists is if c were 0. So we will choose c to be 0 because let's just say we require y of s to go to 0 as s goes to infinity, because we're assuming that y of t is a piecewise function of exponential order. Okay, in that case, y of s is this, and that is a very easy function to compute the inverse transform of. So we get negative 3 plus 2 times t. Okay, so that's our y of t. Now let's check and make sure this actually works. It was a second order differential equation. dE was 3 times y double prime plus 2t times y prime minus 2 times y was equal to 6. Let's check and make sure that's satisfied. Well, if y of t is equal to 2t minus 6, y prime is equal to 2, y double prime is equal to 0. So then we'll have 3 times 0 plus 2t times y prime, which is 2, minus 2 times y. It's a 3, not a 6. And that's going to give me 4t minus 4t plus 6, which is 6. That's the right-hand side. So this function satisfies the differential equation, and the two initial conditions where y of 0 equals -3, that's satisfied, and y prime of 0 equals 2, also satisfied. So this is the function we're looking for. Y of t is equal to 2t minus 3. It's a little tricky at the end because we saw that expression and we said, there's no way I can integrate that. But if we rewrite this, we use integration by parts for that piece, then this piece will cancel with that piece and we're able to solve the differential equation. Okay, so that is standard, what was it? Standard L27. So you will have IVPs with the Laplace transformation, solving IVPs with the Laplace transformation. Those are the type of problems that you see with standard L27. And the forcing function may involve direct delta, or the heaviside function. This one involves a delta function, and the DE may have variable coefficients. If you have a delta function here, then you're just going to do this. You let Laplace transform of little y equal big Y, take the Laplace transform of the differential equation, substitute into your initial conditions, and you get here. And then you're just going to solve for y. Then, as necessary, do partial fraction decomposition to write y of s in a form so that you can compute the inverse transform. And usually that involves partial fraction decomposition, and of course using your table of Laplace transforms. Then after we did that, we did a lot of partial fraction decomposition. We wrote y of s like this, and then we computed the inverse transform. And then once we had our answer in terms of the heaviside function, it's always good practice to write it as a piecewise function. And so that's how we got here. Okay, so that was our first differential equation for that standard. The second differential equation was this one. It had variable coefficients. Now the variable coefficients in our problems will always be polynomials in t so that we can apply this theorem over here. But we'll let the Laplace transform of little y equal big Y. We'll take the Laplace transform of the differential equation. You can do these in line if you want to, or you can do these separately and then substitute them in. That's what I did this time. And then we have substituted in our initial conditions, and then you want to simplify this equation in whatever way is appropriate. Now, since it has a y prime in it, this is a first order differential equation, and my thought is we need to write it in a form so that we can solve it. Typically, these are either separable or linear differential equations. When we write it in the form of a linear differential equation, we see it is truly linear. We've got y prime of s plus a function of s times y equals a function of s. So this is linear in y of s. So then we solve this linear equation using an integrating factor. So we identify p, we compute its antiderivative, e to that power is the integrating factor. It requires a little bit of algebra. We had to use this, and of course, this sort of obvious one, that in order to get this integrating factor simplified as possible. Then we take the differential equation and we multiply it by the integrating factor. We get this. Then if we've done everything correctly, the left-hand side should be the derivative with respect to s of y times our integrating factor. Always check. It checked out. The derivative of this was exactly what we needed it to be. So by the product rule, this was truly equal to the expression before it. Now I've got y times the integrating factor, and then we take the derivative, and that equals this function of s. We want to undo operations until we get y of s by itself. So we're differentiating on the outside. We anti-differentiate to get rid of that. then we look at this and we're like, oh no, we can't do that because we've got -3 times this e to the negative constant times s squared, and that involves an error function. And we don't know how to deal with error functions. They don't have antiderivatives that you can just write down. They're not functions that we've studied in other classes. So we think, okay, and I'm thinking to myself, this is a textbook problem. There has to be a way to handle this. So I'm thinking, I don't know what to do with this. So I'm just going to set it aside for right now, but I know I could handle this with integration by parts. So I rewrite this expression this way, and then I say, okay, I need part of this to be u and everything else to be dv. dv needs to be something I can take the antiderivative of. Well, if this is an s times e to the negative constant times s squared, I can compute an antiderivative. So I let that be my dv. Everything else is u, which happens to be a polynomial. Anti-differentiate, differentiate, then we get uv minus the integral of v du. And because this is a nice textbook problem, the ugly terms cancel. The one that we could not handle is canceling with something that we could not handle as well. So we've got -3 of those over here, we've got 3 of them over here, and they're gone. And so now we just have this plus c equals y times our integrating factor. So we divide by the integrating factor to get y by itself. And then we say, I still don't know what to do with this. But then we say, that's right. Y of s is supposed to go to 0, and this goes to infinity or negative infinity, depending on the value of c. The only time y of s goes to 0 is if c is equal to 0. So we choose c to be 0. Then y of s is this, and then computing the inverse transform is relatively simple. And then we're saying, okay, I don't know if that was really something that we ought to do, because nobody ever told us that y of t had to be a piecewise function of exponential order. But we were assuming that it was when we used this right here. So we said, let's check. Let's check and make sure that y of t actually satisfies this differential equation and also satisfies our initial conditions. So we compute the first and second derivative. We substitute into the differential equation. We get 6. That's great, because that's what the right-hand side of the differential equation is. Then we check the 2 initial conditions, and we see that they're satisfied. Awesome. Okay, so that is how we handle differential equations with variable coefficients, polynomial coefficients, subject to initial conditions with the Laplace transformation.